Alright, my name's Aubrey Rage, and this is my lab number 1 for Physics 2211, constant velocity. So the purpose of this lab examines the motion of a rolling ping pong ball that I chose at a constant velocity. And so firstly, we'll be going over the system, its environment, some assumptions that were made. Then we'll move on to the tracker software presentation, break down that computational model construction, compare what we observed in tracker and what was predicted from the computational model, and then we'll, break down some what-ifs and get into the bigger picture. So firstly, the ball starts off in a closed system where the ball travels at a constant velocity. In order for this to happen, we know that the net force on the ball must be equal to 0. So to achieve this, we assume that friction and air resistance are both negligible, and we sort of get this from Newton's first law, which states that objects in motion will stay in motion, unless acted upon by an outside force. So the formula below are derived from Newton's second law, the momentum principle, and we will sort of see those pop up in our computational model and, explain this a bit more later. So the system sort of works like this. I've provided some hand-drawn diagrams here. So the diagram on the left is the initial push, the initial applied force, where the ball's speed is increasing, and then the diagram on the left shows gravity and normal force acting upon each other, and that net force becoming 0 when the ball is moving at a constant speed and velocity. Now here we can see the tracker software analyzing the motion of the ball. I selected 30 data points along the line from t equals 0 to t equals 1 so that the motion of the ball could be analyzed once every 2 frames, as the video is at 60 frames per second. Another important thing to note is that right is the positive x direction and left is the negative x direction. So now we'll get into the computational model construction. So here's where those two formula used in Newton's second law kind of pop up, and we can apply actual physics into the code. So I left the ball's mass at 1 because the mass is sort of negligible because F net equals mass times acceleration. So we don't have an acceleration, and we know that F net must equal 0, so the mass doesn't really matter. The initial position of the ball starts, I chose the value given at the starting position in the tracker video software, which was so close to 0, but just not quite there. But it's okay, it'll still serve as a baseline for this experiment. And then using a line of best fit and creating a regression, I found that the velocity of the ball to be 0.811, and just plug that in. Our starting time was t equals 0, and I chose 1/30 for delta t, to match up with what we chose in tracker. And yeah, so next we can kind of see the rest of the physics being acted out in the computational model. This is how the program makes its calculations before plotting data, as well as I linked the project down there too. So here we have the graphs where we're comparing what was observed and what was predicted in tracker and the computational model. So we see at the beginning they match up really well with each other, and then the tracker software sort of starts to deviate a little below what should be the perfect condition predictions from the computational model. And there are a couple of things that can account for this that we'll sort of get to break down in the what-if section, but just keep this difference in mind while we go over that. So first, here's some what-ifs. What if we flip the axes? So what if we made left the positive x direction and right the negative x direction? The only change that would occur here is that the slope of our graph would not start at 0 and be positive. So our graph would actually start at a higher value and then have a negative slope, but all of the values would remain the same. Now let's kind of address the difference in velocity that we saw from tracker and the computational model. So what if we did things a little differently, i.e. what if we chose something with a lower friction coefficient, or we took away the possibility of z-directional movement completely? I think both of those things would definitely improve what we saw in the predicted versus observed outcomes, because if we choose something with a lower friction coefficient, then that friction could actually definitely be considered negligible. We're not exactly sure that the net force is equal to 0. I'm very suspicious of that based upon the outcome that we saw. But yeah, those things could address that and bring that net force a lot closer to zero and sort of help those results mesh together much more nicely.